Hello, it's Stat134, Lecture 13. You have Quiz 3 on Wednesday covering Section 2.6, 3.1 to 3.3. Last time we started Section 3.3, where we introduced the standard deviation. Sigma is basically it's the average deviation from the mean, or the square root of the expectation of the deviation from the mean squared. We talked about tail bounds, such as Chebyshev's inequality, which is true for any random variable that has a mean and an SD, and it gives you an upper bound for the tails, and so if it says that the chance of being more than k SDs from the mean is less than or equal to 1 over k squared. And if you want to write this as a one-side tail bound on the right, you could just remove those absolute value signs, put the mu on the mean on the other side of the inequality, and then you would get probability that x is greater than or equal to mu plus k sigma is less than or equal to 1 over k squared. It's the same 1 over k squared because we're not assuming symmetry here. So you can compare this with Markov's inequality, which does assume that x is non-negative, but then says the probability that x is greater than or equal to, so if you did know the SD, it says that x is greater than or equal to mu plus k sigma is less than or equal to mu over mu plus k sigma. And so you can compare 1 over k squared with mu over mu plus k sigma, and decide under what situations one is better than the other. Today we're going to look at another formula for the variance of x, which will lead us to a formula for the variance of x squared. We'll look at a linear change of scale. We'll investigate the variance of a sum of two independent random variables, and look at the central limit theorem. So another formula for the variance of x. Let's first recall that you can pull out constants from expectations. So the expectation of x is just the expectation of x squared. So the variance of x, writing that as the expectation of the deviation squared, if you just FOIL then and you distribute the expectation, you'll see that you get expectation of x squared minus 2 times expectation of x squared plus expectation of x squared. So we have a cancellation, and we just end up with variance of x is the expectation of x squared minus the mean squared. Solving for the expectation of x squared, you get that is the variance of x plus the mean squared, which is quite a useful formula. So then we did an example where let x be non-negative random variables such that the expectation and the variance are both 100. Can you find the expectation of x squared exactly? If not, what can you say? That was a straightforward application of that formula above. So we got 10,100. Can you find the probability that x squared is between 70 squared and 130 squared? So if not, what can you say? So, well, we can say a lot here, just not exactly. So we could use Markov's inequality here, and Markov, probability that x squared is greater than 130 squared is less than or equal to 0.6, and so then the probability that x squared is less than 130 squared is greater than or equal to 0.4, And since the probability of the region that we're looking for is clearly less than just x squared less than 130 squared, we can conclude that a lower bound for the probability of interest is 0.4, but in fact we can do better with Chebyshev. So the thing is that we can't apply Chebyshev to x squared because we don't know the SD of x squared. So we'll have to take the square roots across the inequalities here. Notice that 70 squared, that x squared between 70 squared and 130 squared is equivalent to x between 70 and 130. So their probabilities are the same. And then we just go and apply Chebyshev. And we get a lower bound in this case of 0.89, which is better than 0.4. So we'll take Chebyshev. Then we did a concept test, and the answer here is true. So the most straightforward is to use Markov. So x squared is non-negative. Expectation of x squared is 13. So then expectation of x squared greater than 40 is less than or equal to 13 over 40. Now, some of you were looking for it to be exactly less than or equal to 1/3. That's not necessary. 13 over 40 is less than 1/3. So, in fact, the expectation of x squared being greater than or equal to 40 is strictly less than 1/3. But nevertheless, it is true then that it's less than or equal to 1/3. So true. Using Chebyshev, we could do that. And I'll let you look over these details here. It's similar to above. Just note that what we find here is actually that Chebyshev is not as good. So if we were just to go with Chebyshev, we actually couldn't conclude that it's less than or equal to 1/3. But that doesn't. But just because Chebyshev doesn't provide a bound that's less than or equal to 1/3, that doesn't mean that it's false. It actually just means that it's maybe true, and Markov was what we used to confirm it. So change of scale, pretty simple argument here to show that constants pull out of variances as the square. So they pull out of the SD as the absolute value. And furthermore, adding a constant to a random variable is just translating that random variable, which doesn't affect the spread. So it doesn't affect variance or SD. So in conclusion, whenever you look at variance of ax plus b, just pull out that a squared and ignore the b. Then we looked at the variance of x plus y, where x and y are independent, and we used as our motivation x and y being independent binomials with the same p. And we see then that because the sum of independent binomials we know is binomial, n plus m p, and we had discussed the formula for the variance, even though we hadn't proven that yet. So we can see here that the variance of x plus y is the variance of x plus the variance of y if x and y are independent. Question then, do we need independence? Well, here's an example where clearly we do need independence, because if x is the number of hours a student is awake in a day and y is the number of hours a student's asleep in a day, x and y are clearly dependent. The sum of x plus y is 0. The sum of x plus y is 24, so their variance is 0, because the variance of a constant is always 0. So the formula doesn't hold here, and we do need independence. So here was an example you all did really well on, because I guess I gave the solution out while we were doing it. But I'm sure you would have. So you can just find the expectation and the SD for 3x minus 7y minus 4 just following the rules for expectation and variance. And then here's a proof of the addition rule for variance. And so essentially I told you to read the proof in the book. Just a couple guiding remarks is that if x is a random variable with expectation e of x, shown here, then x minus e of x is just a translation of that random variable to the left by e of x. So that'll clearly have center 0. So the expectation of x minus e of x is 0. And looking at the proof in the book here, I just don't expect you to have any problems at all. Just note where we use independence. So remember that the expectation of, I'll even highlight this here. So the expectation of AB is equal to expectation of A times expectation of B if A and B are independent. That is used here in a important way. So please take a look at this. Finally, we ended with the central limit theorem. So the central limit theorem is considered the most important theorem in probability. Unfortunately, the argument to prove it uses moment generating functions, which is something that we will actually cover later in the course, and who knows, maybe we'll revisit this then. But right now we're not equipped to prove it. Your book doesn't prove it, but it's important to know the statement. And honestly, we've seen an example of this. I'm just going to go ahead to this next slide here, where basically we saw that for binomial, when p is close to half, that binomial looks approximately normal, the binomial distribution. And the reason for that is that binomial NP is a sum of n independent Bernoulli P trials. So these independent Bernoulli P trials are independent and they're identically distributed. They're all the same. So that's exactly what the central limit theorem applies to. A sum of independent, identically distributed random variables is approximately normal. And so it can be any random variables. It doesn't have to be Bernoulli trials. So that's the power of it. It's actually true very generally, but we saw an example of it for binomial. And so here, if we have x1 to xn independent with mean, they all have mean mu and SD sigma, then the expectation of the sum is n mu, and the variance of the sum is n sigma squared, again by independence. So the SD of the sum is the square root of n sigma. And so the power here is that the sum here is going to be approximately normal with this mean and SD, and you can use, you can approximate, for example, if you wanted to find the probability that the sum is between A and B or something, you can use your lookup table to do that once you normalize your sum by subtracting the mean and dividing by the SD. So I'll let you read that, but